Hi guys, welcome to today's Redox tutorial, level 3 Redox, and we're gonna start looking at some electrochemical cells. So in this video, I'm gonna cover the key concepts for this particular standard, as well as how to tackle questions and how to hopefully get an excellence for this particular section. Now just bear in mind every school does the internal a little bit differently, but the fundamental concept doesn't change, so let's get into it. So electrochemical cells, this is a natural way of generating electricity. So and you often see tables like this given to you in the internals, which is extremely helpful. So let me give an example. Okay, so you probably at this stage would have seen the practical. So if I have a beaker and I have another beaker, these are my two half cells, and then I have two electrodes in here. So these are the electrode. Let's just use the ones I have up here. I have let's say if this is Fe and this is Fe2 plus liquid in aqueous ions in there, this is copper, this is Cu2 plus ions in here. So if I can use a crocodile clips, connect these together, make sure some filter paper act as a salt bridge, connects the two things together, then you generate electricity. Okay, so very simple. I do one of my favorite TV shows, Breaking Bad. It involves one particular episode where the two main characters get stranded on a desert, and then they run out of electricity in the car battery. So and then they just use some simple redox principles to save their lives. So very handy stuff. So how it works with electrochemical cells, the key thing that you need to understand, it is spontaneous. So what that means is that if you want that to, like, this is how your battery works. You plug it in and it works. It generates electricity. So every battery has chemicals inside, and when you connect that into a circuit, they start undergoing redox reactions and they generate electricity. So the key word is spontaneous, and the other thing is they generate electricity. Okay, so there are a few ways of looking at this, and I'm going to look at the first. I'm just going to be really pragmatic, and we're just going to use the standard reduction potential values first. Okay, so we got the copper 2 plus, and that there, and then the Fe2 plus, and then negative 0.44. And just before we answer this particular question, like say looking at this particular combination, people always get confused with the standard reduction potential values, but the definition is in the name. It is the standard reduction potential. It is telling you how much in this particular couple, the thing on the left hand side want to reduce to the right hand side. So if I write it out like this, you can see that I'm just going to do 3, and then you can see how similar it is because it's all the same. Can you see I'm just copying the species down? And can you see from the left to right, these are all reduction reactions. And how I can tell, this is +1, this is 0, this is +2, this is 0, this is +4, this is +2. The oxidation number is all reducing. These are all reduction reactions. And that's why it's called a standard reduction potential value. It is asking you, it's telling you how likely is the species on the left hand side wanting to reduce to the thing on the right hand side. And the figures that you see given, the more positive it is, the more likely it's going to reduce. So in this case, if you have copper, you have this combination, and the iron combination, one number is obviously more positive than that, which means the Cu2 plus is more likely going to turn into Cu, and then the Fe2 plus and Fe is going to go the other way. Okay, so this is a quick way. So you're trying to get a loop going, and that's how I tell my student just to not to rewrite the two half equations the same way. Like, no, you don't do two oxidation reactions or two reduction reactions, because by doing this, you know what's turning into what. Okay, so let's get into it. Now, I tend to save that part of examination again later, because you need to understand what those numbers mean in a little bit more detail. But just let's look at this particular question first. So how much electricity is generated is determined by the cell potential. And how do we calculate the cell potential? Is the standard reduction potential of the reduction reaction minus the standard reduction potential of the oxidation reaction. And in the electrochemical cell, this number has to be positive. Okay, so it has to be positive. Positive means this is spontaneous, and it means you generate electricity. So you got two numbers here. Let's just scroll up before I forget what they are. Okay, so one is positive 0.34. So the Cu2 plus and Cu is 0.34, and then the Fe2 plus and Fe was negative point, I think it's negative 0.344. There you go. So if you have a really poor understanding of redox, you can just cheat. You can just, I mean, not physically cheat, trying to cheat in the exam. What you can do is that you can just look at these two numbers and just ask yourself, how am I supposed to use one number minus another number which gives me a positive number? And hopefully this is pretty straightforward, that you can trial and error. There's only two possibilities, is to use 0.34 minus the negative 0.44, which will give you a positive 0.78 volts of electricity. So this is positive. It means it's spontaneous, which means that's how the reaction is going to go. Okay, so let's go backwards. 0.34 must be the reduction reaction. The negative 0.44 must be the oxidation reaction. So literally, you don't really understand what those numbers mean, but you understand that the cell potential has to be positive, and this is a combination. Use one minus the other, and that's the only possibility to get a positive number as the outcome. So that tells you the reduction reaction is a Cu2 plus / Cu, and then the oxidation reaction is Fe2 plus turning to Fe. And once we figured out this, we can then balance half equations. So we know the first one's reduction reaction, so that means my Cu2 plus must turn to Cu, and then the other one is oxidation reaction, which means my Fe turns to Fe2 plus. Okay, so one goes this way, one goes that way, then you form a complete loop, and then balance half equations. Surely you guys can do this now. And this is a balance equation, this is reduction, this is oxidation. So Cu2 plus Fe gives me Cu plus Fe2 plus as your full equation. And then Cu2 plus, this is the oxidant, and then Fe is my reductant. Okay, so and then the other thing they will ask you to do, let's say do the oxidation number. This is from +2 to 0, this is from 0 to +2. So you can explain why is this a reduction reaction, because the oxidation number of Cu is decreasing from +2 to 0, whereas the other one's going from 0 to +2. The year 12 stuff that you've been practicing heaps of last year in year 12 chemistry. This is your full equation. And then observation wise, what I might just save observation for a bit later, but this is pretty much what you're required to do. And then I personally like to go back to my diagram and just come back and decide, okay, let's remember the Fe in this reaction, my Fe was turning into Fe2 plus. So this is the oxidation reaction, and oxidation reaction, so that tells me this side is what we call the anode, this side is called the cathode, because anode, this first letter start with A, and then oxidation is also a vowel, which also so both of the two things start with the letter vowel. That's how I remembered it from high school. I still remember it, even though high school was a long time ago, so that worked for me. I would like to think that will work for you as well. So anode, oxidation. So oxidation occurs on the anode, so that means in the left hand side of this particular diagram, this is anode, it's doing oxidation. And what is actually happening here is that you are generating electrons. Okay, so anode is oxidation, oxidation is losing electrons, loss of electron is oxidation. Okay, so you losing electrons, and the electrons have to go somewhere. So the electrons come out of here, go through the circuit, and then goes into the cathode, where the electrons are required for the reaction to take place. So you can see how it is spontaneous. You need both of them. You need the oxidation reaction to lose electrons, you need the reduction reaction to gain the electrons. Okay, now one other really important thing is that because you're losing electrons here. So this side, I tend to think of it as electron rich. So this is the negative electrode. So because if they're making so many electrons go out of here, or the other way they can remember, trying to understand is that because the electrons are attracted to the positive side, so that means the other side must be positive. So your cathode, your anode in electrochemical cell is negative, your cathode is a positive electrode. Okay, so that's pretty much it. I mean, I don't really want to go into the details of how to how to write a proper like a NCEA, because every school is slightly different, but this doesn't change. Okay, now observation wise, sorry, this is turning into a scribble. Again, depends on your school. I'm pretty sure most schools will give the observations too, as in, you know, what color Fe2 plus is, what color Fe is, what color Cu2 plus is, what color Cu is. So I'm going to tell you that Cu2 plus is blue, copper is a pink solid, Fe is a gray solid, and then Fe2 plus from memory is yellow liquid. Okay, yellow aqueous. So what's happening on the left hand side? So let's go back here. Let's think about this. See, this Cu2 plus, which is blue, and it's turning into Cu. So that means the blue Cu2 plus is being used to make the copper. So that means in this particular reaction, your blue Cu2 plus, the concentration of that's going to decrease. So that means the color will be more colorless over time. Okay, it doesn't happen straight away, because, you know, one thing that I feel that our students don't get trained enough is how to write observations. It doesn't change from blue to colorless straight away. It normally takes quite a bit of time. Okay, and what's going to happen to the copper? The pink copper will obviously get bigger, so you will see more solid. Okay, for the oxidation reaction, the Fe, the gray solid, is being used to make Fe2 plus. So that means the Fe size will decrease, you know, so it decrease in size over time, whereas the Fe2 plus, you have more Fe2 plus being produced from the reaction. That means you have the solution will become more yellow over time. Okay, so that's the observations. Okay, so that's the pretty much the thing that we want you to do. And now some schools are quite big with this. You know how we decided that the Fe, you may be required to draw these cell annotation diagrams or cell diagrams. So this is how I'll just do it really quick. There you go. Okay, so this is a simplified version, because you probably realize chemists or scientists in general are very lazy. We don't like writing all of those writings. So we keep the anodes on the left hand side. This single line here, this is a state separation. So that means the electrodes are on the left and right. And then these two things are aqueous. And what you want to do, you want to put the anode on the left and you want to put the cathode on the right. And the beauty with this is that the reason why I do it like this, I can see, yep, this is oxidizing to that, and yep, this is reducing to that. So from this thing, I can straight away just draw this. Fe is turning into Fe2 plus, Cu2 plus is turning to Cu. Okay, so that should be quite straightforward, I hope. Now, sometimes you may not have Fe or copper. You may have, let's say, let me give an example. If I have, let's say, for example, Fe2 plus turning into Cl2, Cl minus, and say carbon or platinum. It doesn't matter which one you use, but the reason why we use platinum is, or carbon or graphite, is because the Cl2 and Cl minus are both aqueous or gaseous, so they can't conduct electricity. So you need something solid to conduct electricity, whereas the Fe on the other side, it is a metal, it conducts electricity quite well and it participates in the reaction, so you're going to need that there. Okay, so that's the electrochemical side of things. You know, that's the basics. Now, if you want to look at the more difficult part, here it is. Let's bring it back here. Now this is something I want you to, the viewers, because everyone can do those calculations. Like I use this one minus the other one, trying to get a positive number. But you need to understand what these numbers actually represent. Okay, so back to that standard reduction potential stuff again. It is measuring how likely you'll think that this particular half cell is going to go reduction reaction. So out of this combination, out of all of these numbers, I'm going to highlight the most positive one, which is this. I'm going to highlight the most negative one, which is this. So the Cl2 Cl minus is the most positive combination, whereas the other one gives us the lowest or the most negative standard reduction potential. So what does that mean? So that means Cl2 Cl minus combination, because the number is so positive, that means the Cl2 really wants to turn to Cl minus, whereas the Fe2 plus and Fe, because the number is so negative, the Fe2 plus doesn't really want to turn into Fe. I mean, it can, but it just doesn't want to, because it will rather go the other way, because it's, rather than doing oxidation, it wants to do reduction. So by highlighting that, we understand that this, because the Cl2 really want to reduce, this is the strongest oxidant out of everything that we have in this table. What are the oxidants? So can you guys see all these dash in between? If I draw a line along the dashes, oh, pretty good job there. Everything on the left hand side are the oxidant. Everything on the right hand side are the reductant. Okay, so again, I'm trying to train you to think. I'm not trying to train you to write model answers, because if you don't understand, you can't write model answers. So the most common mistake is someone do this. They go Cl2, Cl minus. They write the whole couple together and they say this is the strongest oxidant. If you do that, that straight away is a big cross, because these two is a couple. One of them is the oxidant, one of them is a reductant. So if you have identified the Cl2 Cl minus has the strongest standard reduction potential, which is really obvious, that means the Cl2 really wants to reduce. That means it's the strongest oxidant. So what does that mean? That means the strongest oxidant really want to reduce, and it can oxidize the Fe to Fe2 plus, and itself in turn reduces. Okay. In contrast, the Fe is the strongest reductant. Okay, because the Fe2 plus doesn't want to oxidize. It wants, the Fe instead wants to reduce. Sorry, the Fe2 plus doesn't want to reduce, the Fe wants to oxidize. So hence it is the strongest oxidant, strongest reductant. So what that means is that the Fe is going to reduce the Cl2 to Cl minus, and itself will oxidize from Fe to Fe2 plus. Sorry, we've got a bit mixed up here. I'm trying to record this at midnight, so I'm half asleep. But that's what that's one of the probably the most difficult thing, because sometimes if we give you a question like, say for example, I'm going to use some combinations here. If I give you Cr3 plus and I give you let's use Fe2 plus, for example. If I mix Cr3 plus and Fe2 plus, and the question is this going to react? So reaction, question mark, is this going to react? So that means this is a slightly different variation of the question. I don't know if your school offers this. If they did, this is what you need to think about. You need to find these species in the table, so which we can find in here. So the Cr3 plus is over here, the Fe2 plus is over here, and we have the numbers here. But if you look at these numbers, can you see that the Fe2 plus and the Fe combination has a more negative number compared to the Cr3 plus? So that means if I don't look at the question in particular, can you see the Cr2072 minus is actually a really good oxidant, and the Fe is a very good reductant. So if I had those two, they will react. Okay, and that will give me this number minus this number, which will give me 1.77 volts of voltage. Now, if I have the opposite, if I have the Cr3 plus instead, and I have the Fe2 plus. The Fe2 plus is a crappy oxidant and the Cr3 plus is a crappy reductant. So they cannot spontaneously oxidize and reduce each other, so there's no reaction. Okay, so this is why if you mix certain chemicals and nothing happens, because they're just not strong enough to make a reaction occur. Okay, so hopefully this has been helpful enough. I do realize I go through this quite quickly, because just remember, again, with internals, the reason why I don't like going through questions for internals, because every school do them slightly differently, but the concept remain the same. Okay, so hopefully you guys found this video helpful, and yeah, as always, if you have any questions, feel free to leave in the comment section. Subscribe and share the videos with your friends who are struggling in chem, and I'll see you guys next time. Bye bye.